Okay, is my screen visible to everybody? Hello.
Yes, sir. Yes, sir. Visible, sir.
Okay, okay. Okay. Good evening, everybody. Let's start our today's discussion. So today we will basically focus on the problems of the assignment 3, and we will discuss how to solve the assigned questions. Okay. So let's come to the question number 1. So what type of ring structure is present in structure 3 and 4? So, what is the answer? Is this quinoline or pyrimidine or naphthalene or purine?
Pyrimidine.
Pyrimidine. Okay, what is the structure of pyrimidine? Okay, let's discuss. Okay, what is this first structure? The written in the number 1. What is this?
Purine.
Purine moiety. The common structure of the purine molecule is the heterocyclic ring. One pyrimidine ring is fused to one imidazole ring, right? So this is the common structure of the purine. And what is specific name of this compound? Can anybody say this?
Gonidine.
Six, six aminopurine.
Yes, we can say it's 6-aminopurine. If nitrogen would stay there, sorry, hydrogen, then what we will call it? Rather than this, if hydrogen was here, then what we will say it? You know the structure of adenine.
Adenine.
Yeah, this is the structure of adenine. If hydrogen is there in the 9th position instead of this one, then we will say it adenine. Okay. So what is this structure? This structure 2,
Gonidine.
not guanidine, guanine.
Guanine.
Guanine. Okay. So what are those? What is the significance of this purine and pyrimidine? What are the common structure present in where? They are widely present in. They are active component of nucleic acid, right? There are two common structure, purine and pyrimidine. Two type of bases are present there. One is purine and another is pyrimidine. They together constitute, they are present as a base in the nucleic acids, right? Like DNA or RNA, deoxyribonucleic acid or ribonucleic acid, they are commonly present as base in purine and pyrimidine. Okay, so now tell me what is the common structure of pyrimidine moiety? How many nitrogens are there in pyrimidine moiety?
Two
4.
nitrogens which are 1-3 position to each other.
Yes, two nitrogen which are 1-3 position to each other, right? This one. So is this exactly the pyrimidine structure? Is this conjugated one?
Yes.
How can it conjugated? There is no double bond here. So how we can say that it is a conjugated structure?
One pair of nitrogen is also come in conjugation.
Yes, lone pair of nitrogen is also coming. Okay, so this is a derivative of pyrimidine. This is obviously the basic structure is pyrimidine. The nitrogens are at the 1,3 positions, but instead of the double bond, the carbonyl group is there, right? So this is, we can say, the pyrimidone structure. Okay, so the common pyrimidone structure can be written like this. Okay, so if you can observe that there is a carbonyl group, so pyrimidine, there is a derivative of pyrimidine which is called pyrimidone. Okay, okay, so here the right answer is definitely we have to choose the pyrimidine, this one. But for your understanding, I am just telling you that this kind of structure where a ketone or carbonyl group is present within the pyrimidine ring is called the pyrimidone structure. Okay, got it?
What about fourth structure?
They all are derivative of the pyrimidine. Okay, so that they are just introduced two ketone group instead of one. So they all are the pyrimidone. That carbonyl group is introduced in the pyrimidine ring. Common structure is the pyrimidine. If we have to designate it with the common name, then it is definitely pyrimidine. You know the structure of naphthalene.
Yes.
Yes. Two
How does
benzene
it
rings
look?
get fused.
Two
Two benzene
benzene
rings
rings
get fused.
get fused together, right?
Yes.
Okay. Okay, so anybody has any doubt? Can we move to the next question?
Sir, what is the name of structure number 3 and 4?
Name, this is the derivative, means we have to, they don't have any common name, but they are the derivative of pyrimidine ring, or you can say it commonly pyridone
They,
structure.
it look like a cysteine or uracil.
Okay, yeah, yes, you can say it, uracil system. But in uracil there is a no NH2 na. What is the structure of uracil? The structure of uracil is like this one na. This one na. Uracil is this one.
Fourth number structure and this one is are same.
Okay, yeah. Fourth one is uracil. Yes. Yes, fourth one is uracil. And uracil is present,
Purine, in purine.
no, in DNA or RNA.
RNA.
DNA.
Okay, we will discuss this later. Okay, let's move to the next question. Okay, uh, which of the following amino acids would be most prone to react with the irreversible inhibitor? So, what is the answer? Anybody?
Sir, it's lysine.
Yeah, it's lysine.
But in exam I wrote threonine.
Okay, in assignment you wrote threonine.
Yeah.
Okay, okay. So let's discuss why it is so. So, irreversible inhibitors are electrophilic in nature and react with the nucleophile. So, you
Form
have the idea.
hydrophobic
Sorry,
bond.
anybody is
Methyl
saying
forms
anything?
hydrophobic bond.
Okay, so you have the idea of electrophile and nucleophile.
Yes, electrophile are electron deficient species and nucleophile are electron rich species.
Yes. So it is from the term we can know that it is electrophilic, that it has the philicity or affection towards the electron, right? So definitely it is electron deficient species, and the nucleophilic, which from its name we can say that it is a electron rich species. Okay. So irreversible inhibitors are electrophile in nature and reacts with the nucleophile. All amino acids mentioned contain functional group which could react with the electrophile, right? Tyrosine contains a phenol group, threonine has an alcohol group, and histidine has a
Imidazole.
heteroaromatic ring. Yeah, imidazole moiety. Okay, so the most nucleophilic group is the primary amino group of the lysine. Lysine has the side chain, it has the functional group free NH2, right? Okay, so it in lysine, in the side chain of the amino acid, it has the free NH2 group. Okay, so and we as we discussed that irreversible inhibitors are the electrophilic in nature, that it has the deficient in electron. So, and here we have the nucleophilic center, the NH2 group. It has the lone pair of electron. So it acts as the nucleophile and it reacts with the electrophile so of the inhibitors. So in this way, it can bind with the so lysine has the tendency to bind with the irreversible inhibitor. Okay, clear? So right answer is this clear to everybody?
Yes, sir.
Okay. Okay, so let's move to the next question. Okay, so what is this shown in the picture? What is happening here in this picture? What we can see? What does the following diagram demonstrate? Dimerization Receptor binding, base pairing, or polymerization?
Base pairing.
Base pairing. So how does it happen? How many types of base is there in nucleic acid? How
Four.
many
Three.
common type? Sorry?
Four.
No, I am not asking the number. I am asking just the common structure. There are two types of bases, like one is purine,
Pyridine and pyrimidine.
Pyrimidine.
pyrimidine, pyrimidine. Okay. Okay. So what are the name of the purine moiety?
A2
What are the bases?
adenine and
Adenine,
No, no.
no, adenine and
Adenine, guanine are
guanine.
pyrimidine.
Yes, they
And
are pyrimidine.
cytosine and thymine are purine bases.
Yes, cytosine and thymine are the pyrimidine bases. Right. So in DNA, you are aware of the structure of the DNA. This is the base, right? This one is called the base, right? And this one, what is this structure? This five-membered ring, what is this called? This one,
sugar.
yes, sugar moiety. And this one,
Phosphate.
sorry,
Phosphate.
phosphate,
Phosphate
yes,
linking. Phosphate
phosphate
linking.
moiety, phosphate linking. So the backbone of the nucleic acid is made of one base, one ribose sugar, and one they are linked up by the phosphate moiety, right? So these are constituting the backbone of our sugar, nucleic acids. Okay, and nucleic acids are the main component of our genetic material transmission, right? Okay, so what is the name of this base? This is
T.
this one. What is the name?
Adenine.
Adenine. And what is this one?
Guanine.
How can it be guanine?
It's thymine.
It is
It's
a
thymine.
pyrimidine moiety. This is thymine.
Thymine. It's thymine.
Yes. And what is this one?
Guanine.
It's
Guanine.
guanine.
Guanine. And what is this one?
Cytosine.
Cytosine. Okay, so there is a specificity that adenine always binds with whom?
Thymine.
Thymine. And there are how many hydrogen bonds in between adenine and thymine?
Two hydrogen bonding.
Two.
Two hydrogen bonds are there. Okay, so there is always a specificity that one purine base is always hydrogen bonded with another pyrimidine base, right? And guanine binds with
Cytosine.
cytosine. And how many hydrogen bonds are there?
Three.
Three. Okay, so it is already shown in the picture that there are two hydrogen bonds in between adenine and thymine, and there are three hydrogen bonds between guanine and cytosine. And instead of cytosine, another base is also present there in RNA. What is that?
Uracil.
Uracil. Okay, so is this clear to everybody?
Yes.
Anybody has any doubt?
No.
So let's move to the next question.
Hmm.
Okay, so here is a multiple choice question that which statement best describes the relevance of an allosteric binding site to medicinal chemistry? Okay, so it is more hydrophobic than the normal binding site and accepts hydrophobic drugs in preference to the hydrophilic drugs. So is this true?
No.
No. Okay.
Sir, what is allosteric binding?
Allosteric binding.
About
Okay. Anybody wants to say that what is allosteric binding? Anybody?
in a protein, we are having one is active site and another one is allosteric site. When the drug bind to the active site, that will change some conformation in the allosteric site also. But the allosteric site is other than active site. So some of the drug will bind at the allosteric site and will change the conformation in active site. So it is like agonist, you can say. Antagonist.
Uh,
Sorry, antagonist.
only allosteric in site only can be antagonist.
Maybe it is antagonist, but maybe allo. I don't know, sir, exactly.
Okay, okay, okay. Let me explain. Okay, some. Okay, let me discuss this. Okay, let's suppose this is an enzyme, right? Okay, so this is the active site of that enzyme. Okay, this one. This one is the active site. Okay, so there is another site of that enzyme where a molecule can bound. Okay, so let's draw, see how can it bind. Okay, so let's the molecule is bound here. Okay, so now what is happening next? Okay, we are considering two different situations. Let me draw first, then I will discuss it. Okay, so let's consider two different situations. So this is our enzyme, this one, this one is our enzyme. So this is the active site of our enzyme. And other than this active site, there is some other site which is called the allosteric site of that enzyme, and where a different type of molecule can get bind. Okay, so now two different cases can take place. Let's first concentrate in our first situation. So here, this is the active site and this is our substrate, right? This one is our substrate. So when we can see that if this molecule, this molecule is binding to the allosteric site, then the conformation of active site getting changed here, and the substrate cannot bind to the active site of the enzyme, right? Can you follow it? Hello.
Sir, could you
Yes, sir.
repeat again?
Yes. So let's suppose this is our active enzyme. This is the enzyme, and there is one allosteric site and some molecule. Suppose this molecule is coming and binding to the allosteric site, and we are getting as a result, when it is bind to this site, the active site of this enzyme getting changed. Can you follow this? Here it was like the shape was like this one, and here
Uh-huh,
it is
yes,
getting the
yes,
curved one, right? So here
yes.
the substrate can easily could fit into this active site of this enzyme, but here the substrate could not bind to the enzyme, right?
Yes, sir.
Yes, sir.
Okay, so what we can say this phenomena, this allosteric,
Allosteric binding.
this is definitely binding, but it is facilitating the reaction or retarding the reaction?
Retarding.
Retarding the reaction. So we can say it allosteric inhibition.
Enzyme inhibition. Enzyme inhibition.
Inhibition, right?
Yes, sir.
See, everybody, it is clear to everybody. I can repeat once again if anybody doesn't get it.
Yes, get it.
Get it, everybody?
Yes, sir.
Yes, sir.
Okay, okay. So this is the case of inhibition. Now coming to the second case, what is happening here? Can anybody say?
The active site and substrate.
Hmm.
There is no binding.
Yes. In the first case, the active
And
site, this is
then
substrate
because
and
of
active bind is not compatible one, right?
yes, and because of allosteric inhibition, there is a
Not
formation
inhibition.
of a
There is
huh,
not inhibition. Inhibition is coming later. First, one
allosteric bind
compound is
molecule
binding to the allosteric
binding.
site, and then the active site is becoming favorable for the substrate.
Yes.
right? So there is a
Yes.
bonding interaction between the substrate and the enzyme. So what we can say it allosteric.
Formation of
Yes, it is definitely facilitating the formation of the substrate for the reaction, right? So what we can say it.
actually it increase the rate of reaction
Yes, yes,
because
yes. It is allosteric activation, right? Got it?
Allosteric anti-inhibition.
Allosteric activation.
Yes,
So
sir.
okay, so allosteric site is the other than the active site of an enzyme where a molecule can bind, and it can act in both way. It can go through the allosteric inhibition where there is no binding, and it can also lead to the allosteric activation of that active part. So always it is not the antagonism effect. It can also show the agonistic effect to the enzyme substrate binding reaction. Okay, is this clear to everybody?
yes sir.
Okay, so now let's come back to our original question. So our question was, what was our question? Which statement? Which statement best describe the relevance of an allosteric binding site to the medicinal chemistry? So the first one, we I got answer from somebody that it is not true. Okay. So the second one, a larger variety of the drug structure will bind to the allosteric site than the active site. So is this true or false?
It is false.
It is false. Okay. Okay, so let's see the last one. Drugs can be designed based on the transition state of the enzyme catalyzed reaction. Is this true or false? Okay, so let's see. Drugs can be designed based on the structure of the endogenous chemicals which bind to the allosteric site and control enzyme activity. So, from our demonstration, we definitely can understand that the allosteric site can definitely control the enzyme activity. Okay, so designing drugs to interact with the allosteric binding site allows a method to regulating enzyme activity other than using inhibitors which bind to the active site. Okay, so allosteric binding sites cannot be said to be more or less hydrophobic than the active site. Each binding site is a different in respect and regardless of whether it is an active site or allosteric binding site. There is also no reason to suppose that allosteric binding sites should be capable of binding a wider variety of the drug structure than the active site. So our right answer is this one, the third option. Okay, drugs can be designed based on the structure of the endogenous chemicals which binds to the allosteric site and control enzyme activity. Let's move to our next question. Okay, how many nucleic acid bases on messenger RNA are responsible for coding of one amino acid?
3.
3.
Three. Three. Yes. How can we explain it? Anybody?
Combination of any three nucleotide base code able to code one amino acid, I think.
Yes, so if we take the two bases, then it is not sufficient to cover all the 20 amino acids. Okay, so we need a triplet code of the bases to cover the all 20 essential amino acids for the synthesis of the essential amino acids, 20 essential amino acids. Okay, so here in probable explanation, the two letters in every possible combination would code for up to 16 amino acids. Still not enough, but there are DNA letters provide more than enough combination to code for all 20 amino acids. Codons must consist of the three nucleotides because this gives the cell the appropriate amount of the combination to code for all 20 amino acids with some redundancy. There are four possible bases in DNA, so if each codon was only one nucleotide, we could only code for four amino acids. Okay, so we take combination of these three UUU, UUC, UUA. These are formed. Okay, so the right answer is this one, three. Okay, now tell me this one. What is the significance of base pairing of function of DNA? What is base pairing in DNA? Anybody?
ATGC.
ATGC. Yes. So the one purine base makes hydrogen non-bonding hydrogen interaction with another pyrimidine base. So this kind of bonding interaction we refer as the base pairing in DNA. Right. So what is the function of this base pairing?
The hydrogen bonding between these two bases AT and GC stabilizes the structure of DNA, I think.
Yes, yes. This gives the. Okay, let's discuss. So the first option is it neutralizes the basic groups and controls the cell pH. Is this so?
No, no.
No,
No.
no.
Complementary. Second option. Second
Yes,
option.
complementary allowing replication.
Yes, yes. So in the third option we get it stabilizes the molecule such that the cell lifetime is increased. Is this right?
No.
No. Okay. It prevents water interacting with the nucleic acid bases. Right or wrong?
Wrong.
Wrong.
Wrong. So we have left with the one option that it means that the chains of the DNA are complementary, allowing the replication. Right. So it means complementary base pairing is very important in DNA molecule because it allows the base pairs to be arranged in the more energetically favorable way. It is essential in forming the double helical structure of the DNA. It is also important in replication of DNA as it follows the semi-conservative replication. Like you know the what is called replication.
Hey.
Sorry,
Hmm.
anybody? What is the process replication means? What does mean? Replication means what is?
Multiplication.
Photocopy, yeah. The synthesis of another DNA from the parent DNA, right?
Multiplication.
Multiplication, the increase in the number. So when the replication occurs, this double helix coiling of the DNA gets denatured, and this one strand gives generated to the other strand, and the two daughter DNA are formed. This coil is getting opened with some various kind of enzymes, and from one DNA we are getting the two DNA, and this process is called the semi-conservative replication. Okay, so once it is getting the opened up the structure of the DNA, so in this way it is very much important, this base pairing, for the conservation of the structure in the newly formed DNA. Right, got it?
Yes.
Okay, anybody has any doubt? Then we shall move to the next one.
Proceed to next question.
Okay. Okay, so now tell me answer of this question. Match the following
First.
effects of the reversible. Huh? Which one?
First.
First one. Yes. Can you explain how it is proceed? How we can explain the answer?
Sir, you please explain by using the graph.
Okay. 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 So now let's draw the common enzyme graph of the enzyme catalyzed reaction. So in the enzyme catalyzed reaction, in this x direction, what we plot here? Substrate
Concentration.
concentration. Okay, and in y direction,
Plus velocity. Rate of reaction. Velocity.
yes, rate of reaction, right? So the catalyzed enzyme catalyzed graph looks like somehow this way. So this part, what we call, mark it as
Vmax.
Vmax. And what is this point?
Km.
Km. And this one,
Half of Vmax.
what do we call it in technical term?
No.
Vmax by 2, half Vmax,
Half Vmax.
right? Right. Okay, so let's take the different types of reaction here. So it is normal enzyme. Okay, and this is competitive inhibitor. And this is so what is competitive? The term itself, what does it suggest? That what does it signify? That competitive inhibitor.
When substrate and enzyme they form complex, but at the place of substrate, when inhibitor comes, there is a competition between inhibitor and substrate.
Yes,
This is
exactly.
competitive inhibition.
Yes, exactly. Yes. Anybody saying anything? And the non-competitive inhibitor, there is no competition at all, but inhibition is taking
There is
place.
there is no competition between inhibitor and substrate.
Substrate and inhibitor, but it is after all the inhibition is taking place. Okay, so which one is the right option? So from the graph itself, we can describe that with competitive inhibitor, what I shown in the graph, the reaction can eventually reach its normal Vmax, but apparent Km is higher. So we can, it is definite from what I have drawn in the graph. So, and with the non-competitive inhibitor, the reaction can never reach its normal Vmax, regardless of how much substrate we add. A subset of the enzyme molecules will always be poisoned by the inhibitor, so the effective concentration of the enzyme is reduced. The unchanged Km reflects that the inhibitor doesn't affect the binding of the enzyme to the substrate, just lowers the concentration of usable enzyme. So from the graph, I have already shown that what is the scenario in case of the competitive inhibition and non-competitive inhibition. So by measuring the, comparing the other possible options, so only A is right one. So in competitive one, the no effect on Vmax, increase in Km, and in uncompetitive one, decrease in Vmax and Km. So in linear mix, decrease in Vmax and increase in Km, and in non-competitive one, decrease in Vmax and no effect on Km. So the first option is the right one. Okay, so now there is a picture is given here. So what is this? The picture. Can anybody
DNA.
tell me? DNA. So we have to answer some question with this picture.
These are
Okay.
nucleic acid bases.
Yes. Consider the following representation of DNA. So, so this is as we discussed earlier that this is the base, right? So can you tell me the numbering of the sugar moiety? Here the base is attached. Base is there. So here phosphate is attached. Yeah. another phosphate is attached. So what is the numbering of this carbon?
The sugar moiety, the carbon to which the purine is attached, which we refer as 1.
Okay, 1 or 1 dashed?
1 dash.
1 dashed, because we give 1 to the purine moiety, the numbering of this carbon of the bases, purine and pyrimidine moiety. So we give the numbering of the dashed with the carbon of the sugar moiety, right? And this one, this carbon,
2 dash,
2 dash. This one,
3 dash, 3 dash,
3 dash,
4 dash, and 5 dash.
4 dash. Right?
Yes.
So can you tell me that what group is present here in 2 dashed in case of RNA? What is the full form of RNA?
Ribonucleic acid,
Ribonucleic acid. And what is the full form of DNA?
deoxyribonucleic acid,
So from the name itself, what is present in RNA here in this position?
oxy group, carboxy group.
Oxy. Oxy group is present here in case of RNA, and as it
OH.
is missing, so that is why it is called 2-deoxyribonucleic acid, deoxy. Right? So there is no oxy in presence of DNA. Okay, so let's answer this question. Consider the following representation of DNA. So the statement has the 4 sub questions. Okay, what are the groups shown in the black? The black color one is
Nucleic acid bases.
nucleic acid bases. What type of DNA structure is shown above?
Primary.
Primary. Why it is primary? Why not secondary or tertiary?
I wrote in exam secondary.
Why?
Secondary are generally double helix, and tertiary are
The folding pattern is also
Folding
involved there.
yeah, yes.
So here in our question, see, only one chain is given here. Can you follow it? Only one chain, right? Only one chain. There is no double helix. So for the secondary structure, 2 helix must be present for constituting the secondary structure. So this one is our primary structure of DNA, right? So it is the primary one. Okay, so now the last 2 questions which we have already discussed. What is the structure term used to describe the end of the chain marked with J? What is the J?
5 dash.
5 dashed.
Dash.
Already. So this is, we have already marked with J. Here J is here. So this is the 5 dashed one. And what is marked with K?
3 dash.
3 dash.
3 dash. Okay. So you have any doubt or anything?
No sir, no doubt.
No doubt. Okay. So if you don't have any doubt, then we can end today's session, and we will meet on next week.
I have one doubt that if we want to plot the non-competitive inhibitor, graphical representation of inhibition on competitive, what should be the nature of the graph?
non-competitive and competitive.
Competitive, non-competitive, and uncompetitive.
Uncompetitive. Uncompetitive will be the normal one. There is no competition or anything inhibition in this there one. So that will form the normal enzyme catalyze reaction. And competitive and non-competitive, I have already shown there.
Yes, sir. But on-competitive inhibition is there, uh,
Okay.
and the binding of that inhibitor occurs at what stage exactly with the enzyme?
Okay. So here, if we uncompetitive one, then it is very weakly dependent on the red diagram. Na? If it is not at all doing any competition with the substrate, then it is very much likely to affect the rate of that enzyme catalyzed reaction.
Okay, sir. Okay, sir. Thank you.
Okay. Okay, so if anybody is done, then we can end up today's session here. Okay. So thank you for joining. So we are ending up today's session. We will meet on next week at the same time.
Thank you,
Okay.
sir.
Thank you. Thank you.
ए, कहाँ गया? 2 कल की है।